In this work, we introduce a new domain adaptation technique for simulation to reality transfer called RetinaGAN. We thoroughly evaluate this method on 3 challenging vision-based tasks: grasping, pushing, and door opening, with both reinforcement learning and imitation learning algorithms. First, we visualize simulation and RetinaGAN adapted images within a grasping task. Notice that the textures and structure of objects are preserved. In addition, the robot arm and gripper are always sharp and precisely translated. RetinaGAN builds on top of the generative adversarial network pipeline. We pass a simulated image through a sim-to-real generator network, which is optimized to translate the image to the real domain. We then apply cycle consistency by introducing a real-to-sim generator network to reconstruct the original simulation image. RetinaGAN adds a perception consistency loss. This enforces pairwise consistency between bounding box predictions from an object detection network. We also reflect this pipeline to translate real images in the real to sim to real direction, as shown in the bottom half of this figure. Within grasping episodes, objects in the translated image are generally detectable by the object detection network. However, notice that perfect performance of the detector is not required for the simulation domain. Compared to prior methods, RetinaGAN produces sharper renditions of objects. We visualize this here in multiple grasping episodes by comparing RetinaGAN to a prior method, RL-CycleGAN. A reinforcement learning model trained on RetinaGAN adapted data achieves an 80% instance grasping success rate in real-world evaluation. We visualize the grasping evaluation process in the real world on several grasp attempts. We then apply the same RetinaGAN model trained for the grasping task to adapt images in a new object pushing task. We visualize simulation and RetinaGAN adapted images from the pushing task. This task is located in a similar environment, but there are distinctions like the red goal marker and the orientation of the robot base. When trained with purely simulation data, the reinforcement learning pushing model is able to achieve 90% success rate in pushing an object to a goal location without knocking it over. Next, we demonstrate that RetinaGAN can also adapt images within a conference room door opening task, using an out-of-domain detection model trained for graspable objects. This next video shows that translated images are consistent, indicating that RetinaGAN is resilient to imperfections in object detection. In real-world evaluation, we showed that an imitation learning door opening model trained with RetinaGAN adapted data achieves 97% success rate in opening doors and entering rooms. We visualize evaluation episodes of the real-world door opening task here.